All right, hello everybody. It will be tough to follow Daniel. I also don't have a lot of stickers to share, unfortunately, so please take his stickers. All right, so let me get started. And in particular today, I'm going to talk a little bit introduction and give you an overview of vLLM, what it does, a little bit about the project if you don't know, as well as some recent highlights and technical insights. And I'm going to spend a little bit time towards the end to focus on the work I've been doing with llm-d, as well as on the distributed front. All right, why don't we get started? So on the introduction side, here we go. Our goal is to build the fastest and easiest to use open source LLM inference and survey engine. And this encapsulates itself as being the cross-platform layer, where on the one side, we support a lot of model from day zero, includes Llama, Qwen, DeepSeek, and a lot more, and GPT-OSS. And then on the other end, we make sure all these models work directly on different kinds of chips, such as AMD GPUs. And we also include CPUs and other accelerator as well. But our main focus has been making sure that these new model architecture can map performantly and directly onto the hardware itself. And in a way, we become this one platform to run your model across accelerators and OEMs. And if you look at our GitHub, we had just crossed the 60K stars threshold. And then through a very limited amount of usage data and reports, we're seeing we're running on quite a significant fraction of GPUs today. And some of those are indeed AMD GPUs. So we're very happy to see a lot of production users continue to use it vLLM on AMD, as well as reporting issues and enhancement as well. This is a pretty big community we're managing here, that we have about 800 PRs that opens every month, and then crossing the threshold of 1.7K contributors, and this just rapidly grows over time. And the way for us to manage it is to have more than 50 full-time contributors and maintainers and committers to manage across all these GitHub issues and PRs. And we cannot do this without AMD, of course, as well as a company like Red Hat, Meta, Anyscale, and Hugging Face. Now, if you look at our API, how would user actually use vLLM? There's two main places. One is we offer a Python interface for offline batch inference. This is where you can essentially use it as acceleration for the Hugging Face transformers, where you directly take any models, and then vLLM will be able to run through the prompt at the highest throughput possible on the hardware of your choice. And the second one is a drop-in replacement that you can directly launch as a server, where you swap your application speaking OpenAI protocol just by changing the URL you are talking to, where we make sure there's API compatibility, and you can directly work with any open source model you like. And both of these combined, also as well as more low-level API, give us a lot of ways to directly integrate with RL in reinforcement learning, rollout, and training and reward framework. And this includes, as Daniel mentioned previously, Onslaught as RL framework as well. And we continue to see vLLM to be one of the primary default rollout engine for RL framework to come, both proprietary and open source. And as well as just to touch a little bit on how do we support models. So we support almost all text generation model before they actually come out and release. The reason here is a lot of the companies are training models such as Qwen and DeepSeek and Kimi, or they are actually already have their internal vLLM version working before the model being released. And a lot of these is a back and forth process that would directly work with the model providers to make sure that everybody, the moment the model is released, that you can get your hands on. And as well as for models that directly not optimized within vLLM, we have this very tight integration with Hugging Face transformers that allow you to run and gain access to, I actually don't know how much, thousands or potentially 10,000 models available inside of Hugging Face repository. And this just needs one flag called model info transformers that will let you have one set of code that you can use for both training, references, as well as inference, and accelerated by vLLM. So this together sort of captures our footprint across all the models that are frontier of today. And just a little bit on how do we prioritize for model support. the very first thing we prioritize is accuracy. So as part of the GPT-OSS launch a few months back, we spent almost the entire time while we have access to the model to make sure that, before the release, to make sure we have reproduced accuracy to using multiple evals, multiple ways to check, to make sure that the numeric exactly matches, so that you're actually getting the model that the model provider intended to train and show you. And you'll find this quite surprising, but over time, we do see a lot of mismatches that due to implementation issue. And this is something we clearly prioritize on the accuracy front. And additionally, also definitely performance. The way to show performance, one way I can show you a lot of bar graph and charts. The other way just to show you the infrastructure we have behind performance. On the left side, it is a benchmark dashboard that we built along with the PyTorch team that makes sure every single commit is run through not just accuracy, regression, unit test, and all that, but also with performance evaluation. And this ensures us to track regression closely and make sure that there's no regression on performance and you'll only get better over time. On the right is sort of the infrastructure behind this is very costly. And we're actually spending quite a lot directly in this kind of CI investment to power and making sure that vLLM always stay frontier on both correctness front, performance front, as well as wide coverage on both model and hardware. And speaking of PyTorch, and one way we directly work with PyTorch is we work with the PyTorch team to make sure you're always getting the latest and best feature from PyTorch. And this helps us unlock a lot of hardware compatibility where you can transparently move your workload between different generations of GPUs and different GPU providers as well. And in particular, vLLM recently were running nightly tests against PyTorch nightly. So that means we always make sure the main branch of vLLM matches and run correctly on the main branch of PyTorch. So the moment there's going to be release, we'll make sure this launches really quickly, and you can directly use the latest and greatest feature. So it's not just on-point updates, rather a continuous process. And additionally, since you are here, I assume a lot of you will be going to PyTorch conference. I just want to plug a lot of sessions and events, including the keynote, but also we have some Meet the Maintainer session as well. So we would love to see you there. And just a little bit touch on the technical part. So I'll show you two slides on new things we have been working on over the last few months that we believe are sort of innovating on the trend of inference. On the left is, the first slide is what we call the hybrid memory allocator. So if you have been seeing most of recently, there's a lot of hybrid model coming out. By hybrid model, we mean models that are using not just full attention, they're now using sliding window attention, and sometimes some layers are mixed with state space model, Mamba, or Delta Update Network to actually make sure that we're reducing the quadratic behavior of full attention. And we have been working on this for quite some time since last year, and we're happy to say, like, just a week ago at SLSP, we're presenting our paper. We presented our paper on Jenga effective memory management for serving LLM with heterogeneity. And this work really is a cornerstone of what we call the second generation of vLLM management, of vLLM memory management, where we focus on having the best-of-class support for sliding window, Mamba, full attention, and a lot more to come, where we believe is where attention is heading towards. And the second one is, of course, now you have efficient storage and computation. There's a lot of ways that you need to transfer the KV cache, store the KV cache into external devices. Here we have been working with a team from llm Cache to really build out an interface that you can work towards with storage provider across hardware, across accelerator, to make sure that you can transfer the KV cache in a almost zero overhead way. And this is what we call the KV connector API. As of today, through vLLM native integration or through first-party integration or through llm Cache, you have access to many, many ways to move the KV cache from the GPU to CPU to disk to a global storage system or like accelerated storage devices such as Weka and others. And just to recap on what I just talked about, so vLLM is a project that is for inference systems and fully open source and collaborative in nature. We make sure there's always timely and optimized model support. We make sure there's a wide hardware coverage, as well as a lot of flexible API, making us the default engine for many RL frameworks. Of course, we're always at the frontier of inference innovation, such as making sure we can run with hybrid memory management as well as KV connectors. Now, I will, of course, deeply integrate with PyTorch. And now I will switch gear a little bit and talking about beyond the engine, beyond the single instance of running LLM on a single host of GPUs, what are we investing heavily as a community to scale it up? And there are multiple ways of dealing with this. One way is talking about the engine from the inside out, where I'm going to talk about inference engines and many other things. The other way is to talk about the cluster point of view. So this is typically not the view you think from the hardware perspective, but from the application backend infrastructure point of view, what we typically want to look at is how do you actually approach this problem from Kubernetes. And this is where llm-d comes in. llm-d is really much a native solution, Kubernetes native solution to scale and manage vLLM's workload. And the reason that exists is as of today, before llm-d, there are several projects in the Kubernetes ecosystem trying to target this. But overall, Kubernetes has been designed to scale essentially HTTP requests for web serving and many others. And these typically are fast, uniform, and cheap requests to serve, as you see on the left side. But LLM is entirely different. They are orders of magnitude more expensive, right? And then the QPS is a lot smaller because they're expensive. And those two combined additionally give you, because LLM inference are predictive in nature, every single prompt, every single responses can vary in length and then in terms of resources used. So this really caused a problem on the existing service paradigm within Kubernetes, and how would you actually optimize it for LLM inference that is slow, non-uniform, and really, really expensive. So what llm-d ended up being is this solution built out over the last this year or so to focus on, again, a top-down way, going from Kubernetes cluster into vLLM as a way, how would you orchestrate multiple copies of vLLM inference engines? And it really focused on making it easy to operate, thinking from the operator's point of view, and someone who actually deploys model in production. You want to make sure it's easy to use, modular, resilient, have native integration with everything Kubernetes, so that you can run it on anywhere you can run it, that have a managed Kubernetes offering. You also focus on flexibility, where we make sure there's cross-platform that you can swap scenes in and out, including different kinds of accelerators. And finally, performance is paramount. Right? After all, vLLM makes sure that a single model can be served on a single node or single GPU very efficiently. Now, if you scale it up, you don't want to lose that horizontal scalability. And sometimes because you are serving in a distributed fashion, you can actually even improve on that to go to a better effective, maybe two nodes have better throughput than just one node times two. And just to expand on this a little bit, that as of today, you can actually use llm-d with what we call the vLLM path. That is reproducible templates that you can directly apply to your own Kubernetes cluster that offer intelligent inference scheduling, pre-fill decode disaggregation, flexible KV cache management, as well as wide expert parallelism. Now I'll illustrate some point of this and how this works. So for the intelligent inference scheduling, there are several ways that llm-d can offer this. One on the left you can see is what we call prefix-aware routing. So as a request coming in, we have ways to directly inform the load balancer, again, Kubernetes native concept, which node and which pod, that is, you can also imagine as which GPU do you send the request to. And this is processed through building up the prefix tree as well as session affinity that send events sending from vLLM instance itself to what we call the EPP, called endpoint picker. Essentially, it is a Kubernetes native concept to make sure that you can route the requests performantly. The second one on the right is, of course, you want to do proper load balancing. But this is not your typical load balancing for microservices. Rather, you need to be actually a lot more session aware and understand the exact utilization target. Because if you have been staring at a GPU long enough, a lot of times the GPU utilization is either 0 or 100. It's unlike a CPU utilization where you actually have a directly curve going from 0 to 100%. So given that, we actually need a lot of good signal on how do you actually properly monitor the metric and also inform load balancing and auto scaling. And then for PD disaggregation, we have built in we have built in a lot of optimization to make sure you can transparently transfer KV caches in your network topology and network mesh. And on the wide expert parallelism, this is where we make sure that not just you can run a giant model, a very big model like K-mean K2, which is 1 trillion parameter, on like several nodes, but also across potentially tens of nodes or 15s of nodes, going scaling to a very large extent. And again, this because we made it work on Kubernetes, which is non-trivial, that you can now have this exact reproducible well-laid path to replicate it and innovate on it. And across the stack with wide expert parallelism, there's some small things we did added along the way, learning from the open source nature of the ecosystem. And in particular, the two techniques shared by DeepSeek themselves about things they're doing with how they're running the DeepSeek v3 model and R1 model in production is extremely valuable. So we have worked with the DeepSeek community to add, for example, what we call EPLB, expert parallel load balancer, that periodically rebalances experts within the mixture of expert model, that over time we can improve the balances over time that achieve better performance and utilizations. And additionally, for the dual batch overlap, where you have two batches going concurrent with each other, that you have, and to overlap the communication and computation. So this is all learning from the DeepSeek open source system itself. And finally, I want to share a few highlights and what's more to come with collaboration of llm-d. One is, of course, over the last few weeks, we've already seen this inference max benchmark. We work closely with the llm-d team to make sure that vLLM being used as one of the default engine, comparing against other accelerators, offering this clear, reproducible, continuously updated benchmark for folks to rely on. And we're very much behind this effort to support both the hardware provider, semi-analysis, and everyone around the ecosystem to make sure that there is not just a static point where you see the performance, but it is very much to a model, inference engine, and hardware co-design to make sure you can deliver the best performance in the end. Aider, you probably heard about Aider. This is llm-d ROCm's kernel library. This is actually pretty much already there in production as a default kernel library within vLLM for the past year or so. And going forward, we'll continue to look forward to adding more and more kernels, right? We have added gems, we added MOE, we added attention, but there's so much more to come, especially with the MI355 series, with the MXFP4 integration, as well as going beyond that to see what's more to add. And a new initiative that we're working with the llm-d team on is Mori, that focuses on the networking side of things. While Aider has the kernel kind of problem solved, networking with the llm-d ecosystem has been something that community really are looking for. And this is where I'm beyond excited to work with the llm-d team to focus on this, to make sure that vLLM comes with integration with Mori, and additionally, have this work out of the box in a distributed and clustered fashion. All right, that's pretty much it. I will just close that. Again, our goal is to build this open source ecosystem to support models on different hardware, give you the choice and best performance and best accuracy to go. And you can find us through all the links here, and I'm happy to answer any question after the talk. Thank you so much.